Okay, 4.7, gentlemen, rational functions. So we just finished our polynomial functions, and now we're going to move on to rational, which are going to be pretty similar to the same ideas that we were just working with in 4.6. So rational function, an equation that's in that fraction form. The first fraction rational function that we have here should look familiar to you. That 1 over x, that was one of our basic parent functions, or sections of graph we had in quadrant 1 and quadrant 3, if we're looking at that graph. Another rational function that we will be referring to, 1 over x squared. Only difference in that graph is both sections of graph are up in quadrants 1 and in 2. Because regardless if we plug in positive values for x or we plug in negative values of x, because we're squaring that, our output is always going to be positive, which causes our graph here to be up above the x-axis. So a rational function, just very simply, an equation that's in a fraction form where your numerator and denominator are both polynomial functions. So we're going to actually just go through and we're going to just look at an example and kind of go through our graph of that rational function. I think it will make more sense if we do that. So our first rational function on number 1 is f of x equaling to 3x plus 15 divided by 4x minus 12. Or I could think of that in a factored form if I want. 3 times the quantity of x plus 5 over 4 times x minus 3. And if we want to find an x-intercept, we could find an x-intercept of any graph if it exists. We know we always just set y equal to 0. And if I set my f of x, my y value equal to 0, a rational function, which is in fraction, a fraction equals 0 when your numerator is equal to 0. Recall our OK. And then for this particular case, our numerator is equal to 0 when this 3x plus 15 equals 0, or x is equal to a negative 5. So we have an x-intercept at a negative 5, 0. And I'm just going to plot that over here on our graph. For any graph, if it exists, we can find a y-intercept. And to find a y-intercept, we know we always replace our x with 0. And if we replace our x's with 0 here, plugging in, replacing x with 0, we're just going to get a negative 15/12. Or we always want to simplify. Any opportunity we can simplify, so reducing each of those by 3, I'm just going to get a negative 5/4 for our y-intercept. So I'm just going to make that our negative 5/4 there for our y-intercept. Asymptotes. All an asymptote is a line that your graph is approaching. It's a line where the distance between that asymptote and your graph, that distance is getting closer and closer and closer to 0. Now, vertical asymptotes, our graph will never cross. You can kind of think of it like a brick wall. Your graph will get really close to it, but it is never going to cross that vertical asymptote. And to find the equation for your vertical asymptotes, it's very simply where your function is not defined. And since a rational function is in a fraction form, our fractions, we have restrictions on our domain when our denominator is equal to 0. So for our particular example here, our denominator of 4x minus 12 will equal 0 when x is equal to 3. So we have a vertical asymptote, this vertical line over here, at x equal to 3. Horizontal asymptotes, a horizontal line that our graph is approaching. The distance between our graph and some horizontal line is getting closer and closer and closer to 0. For your horizontal asymptotes, you want to look at the degree of your terms, and you're finding the degree of your highest your highest degree of your x, and you're going to look at the ratio of the coefficients. So for our example 1, we have 4 terms. We have a 3x, a 15, a 4x, and a negative 12. Our highest degree of x is x to the first. And we have a 3x in the numerator. We have a 4x in the denominator. And the ratio of those coefficients is 3/4. So our horizontal asymptote, and a horizontal line is a y equals to 3/4. So I'm going to draw in our horizontal line here, our horizontal asymptote at y equal to 3/4. Now, we're only going to be dealing with horizontal asymptotes if the degree of our numerator is smaller than the degree of our denominator, or if the degree of our numerator is equal to the degree in our denominator. In our particular example here in number 1, our degree in the numerator and denominator were equal. We had an x to the first in the numerator and the denominator. There are asymptotes where the degree in your numerator is larger, but those get into oblique or slanted. So we're only going to be dealing with where the degree is equal, less than, or the same. We'll be looking at other examples for our horizontals. Branches of our graph, basically sections of our graph. So your number of branches that your graph will have will always be one more than the number of vertical asymptotes. So on our particular example here, we had 1 vertical asymptote at x equal to 3. So we will have 2 branches of graph, and we will look at those in a moment when we graph. If we think of just our parent function, our rational function of 1 over x, which has a vertical asymptote at x equal to 0, where our denominator is equal to 0, and our graph looks like that, which is in quadrants 1 and 3, there are 2 branches for the 1 over x graph. This is one of our branches, and this is your other branch. So it's those sections of graph, and it will always be one more than the number of vertical asymptotes that you have. Behaviors. So as we go to sketch our graph, we want to look at the behaviors around some particular values. Now, when we were looking at our polynomials, we looked at the behavior of our graph as we were approaching any particular x-intercepts. So with our rational functions, we are going to look at the behavior as we approach any x-intercepts, but we are additionally going to look at behaviors of our graph as we approach any vertical asymptotes. So we're going to do a little bit more work with our rational functions. And recall when we were looking at behaviors, it was determined by the exponent and plugging in that value into any other non-zero terms. So we had an x-intercept at x equal to -5, and if we go back to our original function, we're going to take that value, that -5, and we're going to plug it into where it did not come from, into those non-zero terms. So we're going to leave the factor where it came from alone, and we're going to plug that value into the non-zero terms, into the other x's where it would not go out to 0. And if we go to simplify, our behavior that we would get is this linear x to the first. That coefficient is a -3 over 32. So basically our graph around x equal to a -5 should be looking like this negative slope line, a -x. So as we are getting close to this -5, the behavior of our graph should be this negative slope line. It should be coming down through a -5 because that's what a -x would look like. We are additionally going to look at the behavior as we approach this vertical asymptote of x equal to 3. And we're going to take that value of 3 and we're going to plug it into any x other than where it came from. So we're going to plug it into those non-zero terms. And so we have 1x in the numerator to plug into, and we're going to leave the x term in the denominator, that x minus 3 factor. And if we were to plug that in, we're going to get this 24 over 4 times x minus 3, or if I were to simplify a little bit more, 6 over x minus 3. And if I think about what that graph would look like, that is basically a 1 over x graph, right? That's been shifted 3 units to the right, and it's got that positive coefficient. So we're basically just looking at a form of a positive 1 over x graph around that vertical asymptote of x equal to 3. And recall, a positive 1 over x graph looks something like that. But we're focusing on the behavior right around the particular root. And if we're looking around the behavior, a positive 1 over x increases on the right side around that vertical line and is coming down along the left side of that vertical line. So on our particular graph here, as we're approaching this vertical asymptote of x equal to 3, the behavior should be looking like a positive 1 over x, meaning on the right side of this vertical line, our graph should be coming up, our y values are getting larger. And as we approach that vertical line on the left side, our graph would be coming down. Our y values would be getting smaller, because that's what a positive 1 over x does. It comes up on the right side of that vertical line and it comes down on the left side of that vertical line. And if we put all those behaviors together and we sketch our graph of f of x here, we know that our graph should be coming down through this -5. We have this y-intercept of a -5/4, and it's got to come down along this vertical line. And it's coming out along this horizontal line, this horizontal asymptote. And on the right side here, it's coming up along this vertical, and it's coming down along this horizontal of y equals 3/4. So it kind of looks like just a 1 over x graph that has been shifted 3 to the right, which if we look at our original equation, that's what we have. And we have 2 branches of graph. We had 1 vertical asymptote, we have 1 branch over here, and we have another branch over here. Okay. So let's look at another example. Actually, take that back. Let's look at our multiplicities real quick. If we think back to our polynomial functions, with our polynomial functions, we kind of had this behavior where if it was x raised to an even degree, our graphs were looking like x squareds, and if it was x raised to an odd degree, then our graph was taking on a behavior similar to the x cubed. Well, our rationals have that same sort of idea. For our even multiplicities, anytime you have a rational where it is 1 over x even, then your graph is going to take on a shape similar to a 1 over x squared, versus if it is 1 over x odd, then your graph is going to take on a shape similar to a 1 over x. And recall that our 1 over x squared, if it's 1 over x even, was something along these lines, and our 1 over x was something along these lines. Okay, so if we look at our 1 over x minus 1 even, where we have this vertical asymptote here at x equal to 1, if this is a positive coefficient of 1 over x even, then our graph would be up here, versus if it is a negative coefficient around x equal to 1, then our graph would be flipped and would be down here. Versus if we had over here a 1 over x minus 1 odd with a positive coefficient around that vertical asymptote of x equal to 1, we're going to be looking like a positive 1 over x graph, which would look something along the lines of that, versus if it is a negative coefficient, 1 over x minus 1 odd, it's going to look like a negative 1 over x, and a negative 1 over x, or a reflected 1 over x, is going to be flipped over, and your graph would be, if you think of that as kind of your quadrants 2 and 4, if you will. That's been shifted over. So all of our graphs are either going to be, with our rationals, are going to take on the behaviors of positive 1 over x squareds or negative 1 over x squareds reflected, or positive 1 over x's or negative 1 over x's. So similar ideas to our polynomial functions. So let's look at one more example, and then we will take a break. If we look at example 2, it is rational. It's in that fraction form. First thing we want to do is look for any x-intercepts. And x-intercepts, we always set y equal to 0, and our fraction equals 0 when our numerator is equal to 0, and a negative x equals 0 when x equals 0. So we have an x-intercept at 0, 0. Our y-intercepts, we always set x equal to 0, and if I set x equal to 0 here, I have a negative 0 over 0 plus 2 and 0 minus 2, and I basically have 0 over a negative 4, which is equal to 0. So my y-intercept is that same point, 0, 0. It's both our x and our y-intercept here. We want to look at any vertical asymptotes, and recall your vertical asymptotes are where your denominator is equal to 0, those restrictions on your domain, and our denominator is equal to 0 when x plus 2 equals 0, or x equals a negative 2, and when x minus 2 is equal to 0, or x is equal to 2. So we have two vertical asymptotes, one at a negative 2 and one at a positive 2. And our horizontal asymptotes are where we're going to look at the ratio of the coefficients of our highest degree of x. And if we look at our problem here, if we were to think of this multiplied out, this would actually be x squared minus 4 in the denominator. So our highest degree of x is x squared. We have 0 x squared terms in the numerator, and we have the 1x squared term in the denominator, and the ratio of those coefficients is 0 over 1, or 0. So we have a horizontal asymptote at y equal to 0. And I'm going to come over here under example 3 and sketch this. So we had an x-intercept at 0 and a y-intercept at 0. And I'm going to spread this out a little bit here. We have two vertical asymptotes. We had one vertical asymptote at x equal to 2. And we had another vertical asymptote over here at x equal to a negative 2. We had a horizontal asymptote over here at y equal to 0. And if we look at our behaviors, we're going to look at behaviors as we approach any x-intercepts, and we had an x-intercept at x equal to 0, and we're going to look at behaviors as we approach any vertical asymptotes. We had a vertical asymptote at x equal to a -2, and we had a vertical asymptote at x equal to a +2. So we're going to look at 3 behaviors. As we approach x equal to 0, x equal to 0 came from the factor of a -x. We're going to leave that term alone, and we're going to plug 0 into the other x, the other non-0 terms. So we would have 0 plus 2 and 0 minus 2, or we would get a -x over a -4, or a positive x over 4, which a positive x, or x to the first, is basically a positive slope line. So as we are approaching x equal to 0, our graph should be coming up in this positive slope type behavior. If we look at the behavior as we approach the vertical asymptote of x equal to -2, well, that came from the factor of x plus 2. So we're going to leave that factor alone, and we're going to plug that -2 value into the other x's where it did not come from, those non-zero terms. So we're going to have minus a -2 and a -2 minus 2. So we're going to get a +2 in the numerator, this x plus 2 factor, and a -4 in the denominator, which that is, we have a negative coefficient there. So basically we're taking on the behavior of a -1 over x. And if you recall, a -1 over x, a reflected 1 over x, would look something along those lines. So if we go to graph that behavior as we approach this vertical asymptote at x equal to a -2, as we approach that vertical line from the left side, the graph should be coming up. And as we are approaching that graph from the left side, that graph should be coming down, or y value should be decreasing, because that is what a reflected 1 over x graph does. It comes up on the left side over here and comes down on the right side of that vertical line. And our last behavior that we're looking at is as we approach the vertical asymptote at x equal to a +2. And x equal to a +2 came from that factor of x minus 2, so we're going to leave that factor alone. We're going to take that value of 2 and plug it into the other x's where it did not come from, those non-zero terms. So we have the minus and then the 2, and we have the 2 plus 2, or if we were to simplify that, we basically have a -2 over 4x minus 2, or again, simplified, a -1 over x. So our general idea is that negative coefficient, or a -1 over x graph. And again, that -1 over x graph looks something along the lines of that. So if I sketch that on our graph over here, as we are approaching this vertical asymptote, we want that -1 over x behavior. So as we are approaching x equal to 2 from the left side, we see it's coming up. So our graph should be coming up. And as we are approaching it from the right side, we see a reflected 1 over x comes down over here. So our graph should be coming down on the right side. So if we put all of those behaviors together, we should be coming along this horizontal asymptote, coming up along the left side of that vertical asymptote. It should be coming down on the left side of this vertical asymptote, coming up through this x-intercept, and then coming up along the left side of this vertical asymptote. It should be coming down along the right side of this vertical asymptote, and then coming up along the horizontal asymptote over here as it goes off towards a positive infinity. And there is our graph of f of x equaling a -x over x plus 2, x minus 2. Now you can see here in the middle that we did cross our horizontal asymptote. Vertical asymptotes, you will not cross. Vertical asymptotes, you can cross. But as we approach, as we're going off towards a positive infinity, our graph is getting closer and closer to this horizontal line of y equal to 0. The distance between our graph and that horizontal line is getting closer and closer and closer to 0. So it's approaching that value of 0 from underneath. Versus over here, as we go off towards a negative infinity, our graph is getting closer and closer to this horizontal line of y equal to 0. It's approaching that value. That fraction is approaching that value, but it's just approaching it from above. So it did cross here temporarily at 0, 0, but over a large domain, the value of this fraction is getting closer and closer to 0 as x is getting very large or as x is getting very small. Okay, we're going to stop here and we're going to let you try and do number 3, and then we'll come back for number 4.